All right, we'll wait a few minutes just as people are continuing to trickle in. But if anyone does have something they'd like to share, or if you'd like to just state your name and say where you are, we'd love to say hello. And while we wait, I'll go ahead and kick us off with a glue joke. Something that, why was the PCB so chilly? And if you want to put your guesses into the chat, we'd love to hear. Why was the PCB so chilly? Because it didn't get its conformal coat.
Too good. Proper groaner.
Proper groaner.
We're going to be collecting feedback for new PCB manufacturing jokes at the end as well. So that's on our list. Stay tuned for that.
Yeah, we're trying to bond over some super glue puns. So please share if you've got them.
Yeah, I mean, we're really trying to make sure this content is as sticky as possible.
Oh, this is good. You guys are too fast on your feet. I don't know if I can.
Yeah. Are you glued to the ground?
Yes. Joel, you have a new career ahead of you. Just writing puns. You just need to be writing puns.
That's
constantly.
what my career is built off of. Let's go ahead and kick things off with what people are actually here for. I'm sure they're enjoying the puns, but let's share some in-depth technical knowledge about adhesives. So today's agenda, we're going to go through a few introductions for our speakers here. We're going to talk about why we're even talking about glues. Why are they so important? Why do we use them? Why are they such a pivotal part of the manufacturing and product design process? We're going to talk about some best practices, about the chemical composition of the types of adhesives you should and could be using, about surface quality best practices, and best practices regarding the application process and ways that you can QA things to make sure that any adhesive issue that you may be experiencing doesn't propagate throughout your line. And finally, we'll share a couple of real customer stories based on our experience, and then we'll open things up to a live Q&A. So if you have questions, please do put them into the chat. And if you have to duck out early, we will be sending a recording, but please do fill out the survey that will pop up at the end just so that we know how you enjoyed today's content and what you want to learn about next. All right, so I'm going to kick things over to Tobias and Lucas if they'd like to just introduce themselves, and I will bow out into the background.
Thank you, Joel, and welcome to everyone. Thanks for joining us. Again, reminder, if you missed it, would love to hear down in the Zoom chat. Number one, make sure you're sending it to panelists and attendees, and tell us about your trickiest glue application that you've had to work with in the past. And throughout, feel free to just shoot questions for us, and we'll have some time for questions at the end. So I'm Tobias, mechanical engineer by training. I did product design for about 6 years back at Apple, worked on 4 generations of Apple Watch and 2 of iPhone. And now I am at Instrumental leading our solutions architecture team. And I'm joined here by Lucas.
Thanks, Tobias. Hi, guys. Thanks for joining today. My name is Lucas Dillingham, VP of Sales and Senior Application Specialist at BTG Labs. I've been working really in this area, I'll really say of surface analysis, adhesion troubleshooting really for the last decade. So really excited to kind of share some real world experiences and some of the lessons that we've learned along the way.
All right. So why are we so excited to be talking about glues and adhesives today? Well, as a lot of you guys probably know, glues are in just about every modern product. Some type of glue, some type of adhesive is likely being used to build that product. And the reason is the variety of different applications that can be accomplished with these glues and adhesives is massive. So examples, again, environmentally sealing, exteriors of devices, thermal interfaces inside of devices, even just simple fastening of internal components, but in particular, when you're looking at complex surfaces or really tight spaces. And again, these are just a few of them. Lucas, what have you seen in the trends for applications?
You know, big thing in terms of, I'll just say trends of hardware assembly is driving towards simpler assemblies. So literally less parts, being able to take advantage of some of the high performance and lighter weight materials, you know, whether that's from composites or thermoplastics, or say even magnesiums, et cetera. You know, and also consumer requirements around aesthetics are really kind of driving us to figure out, you know, faster, better, easier, cheaper ways to assemble things. But then also allow us to take advantage of thinner materials, right, for lighter weight. This is a big thing that you see, huge trend that you see in, I'll just say, mobility applications, whether you're looking at like air vehicles or ground vehicles. It's huge, right? I mean, if we just look at electric cars for a second, if you look at a Volkswagen, the ID.4, the new electric Volkswagen, it has about 10 pounds of fasteners in its battery pack. If you look at the Tesla, the battery pack is actually glued, the whole housing is glued, saving about 10 pounds of weight, which in an e-mobility application is a really big deal. And why does Volkswagen put fasteners in it while Tesla actually glues a battery pack? Well, it's because Volkswagen doesn't trust the adhesion process. And we'll get into that here in a little bit. But certainly the trends are, we need to figure out simpler, faster, cheaper, more high performance ways to put things together. And adhesives are really it.
Excellent. Well, yeah, the good news is very wide variety of applications, but with that comes a variety of different issues that we have to tackle. And just to give a sense of the scale of these issues, we collected 3 million data points from instrumental customers. This is from ramp and production units over the past couple of years. And of those, the number one issue was glue issues. And this added up to about 0.7% of all units, so pretty significant. And the types of issues, again, huge variety of different issues, overflow, missing, misplaced, all the common ones, and also some bizarre ones. And fortunately for these specific use cases, they were able to identify these issues with instrumental and then address them, prevent them from actually being shipped. But for other applications where they might not have this type of coverage, this could be a significant number of issues that are escaping into customers' hands. Lucas, have you seen similar types of issues?
Yeah, I mean, this is we get involved a lot. I'll say in a firefighting mode when a particular program is going through ramp or launch and they're getting adhesion failure, right? And it can be hard to pinpoint exactly where it's coming from. And if somebody were to come and ask me anecdotally, hey, like what do you see? One of the things I'm going to pick up on immediately is say, God, you know, adhesion failure is a huge issue, right? And typically we deal with it. We try to figure out what's going on, but they're very hard to root cause. So it's actually really cool to see your guys' data here, just kind of really backing up what my gut check would have said. So I think that's pretty cool. Not cool for the people experiencing it, but you know, everyone likes to be validated.
Yeah. So let's talk about why is it so difficult? Why do so many different companies struggle with optimizing these glue processes? I can share one story that's burned into my mind from my days back at Apple. There was one specific application where we had a flexible printed circuit that was coming off the touch sensor, and we wanted to bond it to the housing. This is to prevent translation during a drop of the phone. This was on iPhone. And the number of different variables that we had to take into account when we were optimizing this was just off the charts. Again, this was in a very tiny space. So we were looking at, even just to start off, the basic glue composition different curing conditions, different UV wavelengths, then just looking at compatibility with the surfaces, contamination of the surfaces. And that's just the nominal. Then you have to look at, did you actually dispense what you think you dispensed? And all of these things are very difficult to actually quantify, these kind of amorphous glue blobs. And the insane amount of resources still blows my mind that went into all these different experiments to optimize this one glue process. Lucas, have you seen a similar process elsewhere?
Yeah, I mean, when you're trying to do failure analysis on a failed bond, I mean, there's typically there's some good mental models that you can go through to really try to pinpoint that issue as quickly as possible. And I'll get into specifically what the three inputs are here in a second. But usually, right, if we're looking at a bond failure, first we have to identify where is that failure really occurring, right? Is it within the bulk substrate on either side of that, or is it within the adhesive? Or is it failing interfacially, where that adhesive is just peeling right off the substrate? Understanding where that's coming from, and sometimes it's not just visual. I mean, sometimes you really have to either use some microscopy or even spectroscopy to really understand how that's working. But understanding where the failure mode is it interfacial? Is it cohesive? Is it some percentage of both? Is it mixed mode? That helps drive towards where the root cause might be. And so, yeah, it's can be a tough thing without some previous experience on how to do that. It can be really tough to look at. There's a lot of variables there.
Excellent. All right. We got a few questions. I was just going to answer one here. Is it possible to check for wrong glue is being used by a CM by Ahmed? There's definitely a lot of possibilities of how to do it. I think the question is how to do it consistently, proactively. I've used in the past to check for a contamination, maybe an FTIR to look at the composition. Lucas, what would you say is the easiest way to maybe double check what type of glue is being used by your CM?
Yeah, to make sure that the appropriate glue, well, hopefully they're reporting what glue they're using and that reporting is accurate, but barring that, then yeah, FTIR could be one way where you could actually check like what is the chemical composition of the adhesive itself. You could put in some kind of requirement for them to send that. As an example, in the aerospace industry, they will use XRF to determine that the metal alloy is appropriate. Say you're sourcing aluminum from a foreign country and that aluminum is going to go into a 787, you have to validate it with XRF to say it is the appropriate alloy and has the right structure. So there are tools you can use to do something similar like that.
Perfect. Let's talk about, you just alluded to this, Lucas. Mm-hmm. Let's go back on the other slide just for a second on the failure analysis process, because this is really the heart of what makes doing FA so tricky. Is in particular when something does go wrong after you've optimized all these variables, typically you need to disassemble the device to do your analysis. And in my experience, either you have some heat to loosen the bond, or an extremely cold chamber. Then you could pop off, let's say this is like the front of a phone. But the issue here is then oftentimes the evidence is damaged. So like Lucas was mentioning, you can glean a little bit of information about maybe which bond broke first, but oftentimes it's not conclusive as to what the root cause is. Maybe you get a hypothesis and then you need to do additional experiments to validate that. It's a very manual, trial and error, iterative process to do this failure analysis.
Mm-hmm. Yep. And one thing I would add to that is when you're making millions of units of a device, having to do FA all the time, not only is it tough to even do correctly, it's a huge time sink. It's a huge time sink. If we took it to the flip side to say, hey, what's a low volume, high criticality application? If I look at a circuit board that's going to go into an aerospace and defense app or an aircraft or even some safety critical components that go into vehicles, they don't have the luxury of doing FA on anything. They have to they basically have to control their inputs to get a reliable and repeatable output. And we're certainly going to be talking about that here in a couple slides.
Yep. All right. And we've talked a lot about the tricky glue process, but really this applies to a lot of adjacent manufacturing processes as well. Thermal greases, conformal coatings on PCBs, solder, other PCB underfills, they all have these same sensitivities and complications. This is probably not even a comprehensive list. Lucas, you've probably seen others that you could add to here.
Yeah, definitely. I mean, it's the term, or I should say the phrase that we use here internally a lot is surface critical process. What are the processes that require kind of the same basic 3 key inputs to be successful and reliable? When we're talking about certainly like electronic hardware, these absolutely come up. Thermal greases, conformal coating, oleophobic coatings on screens, hydrophobic coatings to just help environmental resistance. These are all things that depend on really kind of the same 3 key inputs.
Perfect. Let's go ahead.
So look, I can actually jump in here because I've got a couple slides here that are BTG Labs specific. And, I really kind of want to bring the conversation back to, from the perspective of an OEM or a CM trying to actually build these things day in and day out. And when we really break it down, there's 2 main problems in all of these processes, right? At least at the end of the thing. Problem number 1 is that what should stick doesn't, right? Glue doesn't adhere the way you want it to, when you want it to, under the conditions you want it to. And then on the flip side, what shouldn't stick does, right? If we don't have an oleophobic coating that goes down correctly, or a hydrophobic coating that goes down, like say in a solder mask or something, all of a sudden we've got things sticking in areas that we don't want them to. And so our goal, right, BTG Labs' goal is to really help manufacturers control these surfaces with scientific predictability in the factory. And so we're going to get into really how we do this from a technology standpoint, as well as some of the fundamentals. So really the way that BTG Labs approaches this is one of the first things we got to be able to do is we got to provide access to surface quality data in the factory, right, in the factory floor. And people really aren't doing this in a meaningful way right now. We combine that with expertise with a specialized materials and process team based here in Cincinnati, Ohio. We've got a lot of experience in process selection and optimization for how to prepare surfaces, how to apply particular adhesives, what adhesives to select. And then we've got a surface analyst platform that allows us to get objective data in a variety of manufacturing scenarios, right? So this is kind of how we approach the problem. So, when we think about the life of a product team, and of course I'm highlighting a particular cell phone here in this example, but this happens whether you're painting the Ford Bronco roof or you're trying to make sure that you don't put circuit boards in the Hubble telescope that are going to completely fall apart in space. This stuff has real impact, right? I mean, if we look at the Google Pixel, all right, they had a major issue that was well documented, as consumers are wont to do, on Reddit and Facebook, and particular links about the back panel peeling off, right? Typically right around the upper right-hand corner of the back panel of the phone. So we get loss of consumer confidence. We've got a real high warranty rate, right? There were other issues with this phone as well. We've got and then we've got the OEM implications of the staff trying to triage this, where say they're doing development in California or one country, the CM maybe in China, trying to work through the time zone, the flights, trying to figure out what the heck is going on. And at least in this particular phone, it was so tough, along with this and a couple battery issues, that they discontinued it before even releasing the next product. So this was a major challenge for this particular manufacturer. And Tobias, I know I'm sure you've had some stories either during launch or during production where this kind of stuff has really popped up. I don't know if you want to comment.
Yeah, there's countless stories. Luckily, most of them were resolved during production, but really that last bullet that you have there on the countless hours of stress and firefighting really resonates. Another particular story that I remember on Apple Watch. I think it was the first generation, working on the cover glass. The front screen is adhered down to the housing via a PSA, a pressure sensitive adhesive. And of course, this is critical for the water seal of the device. And during reliability testing, we had just a small number of screens that were just popping off during drop testing, water ingress testing, and we could not figure out why certain populations were failing and others weren't. And this is always the dilemma: is, you know, the nominal bond works well, but the variability leads to some outliers failing. And after, again, countless hours of investigation, we determined there was a small trace of silicone contamination on the adhesive. And for any of you that have dealt with this, silicone contamination is not great for any type of adhesion. And
X-nay, silicone is the worst.
And it gets everywhere, no matter how hard you try. And we traced it all the way back. It wasn't even at the final assembly. We traced it back to the adhesive has a release liner on it, just a protective film that it's shipped with before it's installed. You know, the little blue PF that you peel off. And in that PF, they were using some silicone as a release agent to help it peel off easier. And that trace amount from that one vendor, from that one adhesive, caused us just countless hours of running in circles trying to figure out why these were popping off. So it's the smallest thing.
That's a classic story, Tobias. I mean, if that silicone isn't cross-linked enough on the release side, it will transfer. It migrates. It migrates around. And we've worked with tape manufacturers actually to set up inspection requirements on the release liner to check for that migration, because it happens, right? People have run into it, and maybe you were calling up the PSA vendor and saying, guys, we got an issue, and I was helping them on the back end. It's possible.
Silicone is pretty much a taboo material, even if it's used in the proper application. You know, in the PD world, if you mention silicone somewhere, someone's going to have a little
heart
gut
attack.
reaction of
heart attack. Good. So, I mean, this is something we've all experienced, right? It's Tobias has certainly lived it on one side of the equation. I've lived it on another side of the equation. But why does this really happen? And it continues to happen. And it really happens for two reasons. One is we lack predictability, okay? Production and reliability decisions are really reactive and experience driven. Oh, we used this adhesive on the last program. Let's go ahead and use it on this one. Or we used vendor A and we never really had too much of a problem. So let's go ahead and use them again with whatever process they decide to use. We don't have great objective monitoring and visibility of real-time surfaces on the factory floor. And we'll talk about how we do that here in a second. And really the adoption of smart factory tools has been limited in these particular applications, right? Which is where companies like ours and Instrumental kind of come in. The other thing is we really lack a common language. You know, there's functional silos within the organization between, say, product development and manufacturing, engineering, and quality, right? Product development can set up a great bonding process in the lab, but then scaling that to a distributed supply chain introduces a lot more variables, and things always happen, right? You guys may have dealt with organizations in the past where there may be some tension between, say, manufacturing and PD because of previous misalignment, right? And then beyond that, we've got misalignment among the supply chain, right? Suppliers may not really have a great understanding of what are all the process variables they need to be aware of, what are the surfaces they need to create to have reliability, say if they're creating that material and that surface and then shipping it to the CM for final assembly. And then we also don't have external technical cleanliness standards that really deal with chemical residues, really surface chemistry, which is a primary driver for adhesion success. There's plenty of technical cleanliness standards around particulate counts, and really people think about like cleanliness and surface condition from a physical sense when we're talking about general industry, but chemistry is really where it all happens. So we lack predictability and we lack a common language, right? So we have to tackle those two things.
Yeah, I remember, Lucas, on the common language part. We struggled as well. We would try to put in on our drawings for certain parts. You have your list of kind of standard OQC checks, and we would try to put in something that alludes to the surface quality for adhesion purposes, but we could never rely on what that data. We didn't have a defined testing SOP. We'd throw in, sample 3 parts per lot to get water contact angle. And there was no sense of uniformity between vendors. And so it ended up being not an extremely useful metric because it wasn't aligned what the data means from there.
Yep. You need to set baselines of kind of 3 key inputs that we'll talk about here on the next slide, and then scale those through either an SOP or product drawing or control plan or something like that. So let's talk about the 3 key inputs that we help manufacturers really drive to that get us to that ultimate reliability and predictability in a surface critical assembly. One is the properties of the adhesive. Okay, the adhesive that you're buying from Henkel or Loctite or H.B. Fuller or 3M has to be controlled. And usually they do a pretty good job of this, even though Tobias did just tell a horror story of some PSAs he was buying. In general, they do a pretty darn good job. I mean, if you're talking liquid adhesives, Henkel's controlling monomer ratios to a couple %. And you get the batch and lot and manufacturing information of that. The second critical thing is the surface that you're going to apply that adhesive or coating or sealant to. All right, and really what matters is the top 1 to 5 molecular layers of that surface. And this is a key point, and I will say a key hole in the understanding of this whole process that certainly CMs don't have any kind of sensitivity for. If I can see a fingerprint on a surface, that's 10,000 molecules thick, right, roughly. I really care about 1 to 5, 1 to 10 molecular layers on a surface. And then thirdly, we've got the adhesive application. Do we have the right conditions for the physical application of this thing? Curing parameters, the environmental conditions, whether we're doing a UV curable or what have you, pressure, some kind of fixturing. And usually that stuff from the physical application side is pretty well controlled. So as a whole, steps 1 and 3 are being done pretty well, but step 2 really isn't, right? Tobias just mentioned this. It's been tough to get real good standards and just easy to adopt digital inspection methods for surface condition, surface cleanliness, if you want to call it that. So if we control these 3 and we've got digital inputs around all 3, that adhesive joint or that coating is going to perform exactly as we're engineering it to perform, right? This is how we put an airplane wing together and guarantee it's going to fly, right? Literally. So we're going to take that same kind of mental model and that same mental framework and apply it to when we're making millions of parts of, say, a consumer electronic device. So when we're looking at surfaces, all right, and sorry, Joel, I didn't prompt you to change the slide there, but when we're looking at surfaces, we can break these things down into what we call critical control points, all right? And Instrumental has a very similar way of looking at this, where we've got basically, there are particular areas in our manufacturing workflow that can either create the surface we want, or they're areas of high risk where our surfaces can change negatively. So we have the incoming material that could be coming from a vendor or a supplier, or it could even just be upstream, say in the room over, the building over. We've got storage and inventory and material handling of that material, right? We're going to wrap this thing in some kind of packaging material. It'll be maybe in a tray, maybe it ships in open dunnage, however it looks. We've got a particular cleaning process that we're going to institute, right? Sometimes we try to make our vendors clean, but then it gets stored and packed and handled, and then we do something with it. And then we may institute a surface activation step, right? So these kind of four basic things are really where we see things happening all the time. And Tobias, you probably have some experience here that you can share around this.
Yeah. I think from my experience, typically it's a very reactive model, which is not great. Is we're working at that final step. We're working at final assembly. We have some tests in place, and something goes wrong, and only after the fact do we start tracing back through the supply chain and look at all the different points that could affect the end outcome here. So being proactive about setting up these proper quality checks throughout the supply chain is hugely beneficial. Again, we'll talk about it with instrumental, but collecting data to help you trace back when something does go wrong, then you can actually trace it back. Otherwise, you don't have the data, and then you're scrambling around firefighting to try to trace back and collect all the data before you can even start your analysis process.
Yep. Having the digital models key, right? You guys have all heard the kind of the buzzwords, the jargon around digital thread, digital twin. It's the only way you get to be proactive, right? I mean, it really is. And so I'll say this, during launch, the number one issue that we see during launch is not our cleaning step that we've instituted. It's not how we're putting the glue down. Something changes in the incoming material, either through storage and inventory, or the vendor who swears up and down that they're not using mold release is actually applying WD-40 to the steel tool because it helps it not rust. But they don't call it mold release, right? So I mean, I can't tell you guys how many times we find that. It happens on almost every program. A lot of times the difference is how quickly we identify and how quickly we fix it, whether or not it really causes you a lot of pain. So by building a digital thread through monitoring really these three key inputs, we now get to bring surface inspection and surfaces really into the digital age, right? All of a sudden, cleanliness and surfaces can really become part of your statistical process control plan. We get documentation, we get trackability, we get data aggregation, right? Tobias will be able to clue us in onto how we can take metadata around this. So BTG Labs tries to do this with a pretty specific piece of technology that we found really useful for our customers. We can go to the next slide, Joel. All right, and what this is the Surface Analyst inspection platform. All right, everything from a portable handheld tool to auditing for production and quality to completely in-process inspection, where we're able to get really digital cleanliness information in under 2 seconds that anybody can deploy, right? Single button operation, right? What's really cool about this, and I know Tobias will get into this, is that Instrumental can actually take this kind of data in and apply it to their digital models.
Yeah, I'm excited to see the in-process 100% inspection. Yeah. That's pretty impressive. I think you're going to talk about it next about how it works. But yeah, in my background, we never had surface quality 100%. It was always maybe you'd get the QC, the auditing, the 3 parts per batch. But I would say 90% of the time it was in reaction to something going wrong. Whereas this is a more proactive approach of you've taken learnings, you've taken expertise, and these are going to be the critical areas, like a more thoughtful approach to quality control.
Well, let's get a trend line. You know what I mean? Like, what happens during 3rd shift every Wednesday that causes me failures? Like that's exactly how it happens. It's like everybody's experienced glue issues, and we can sit here and like talk about, oh, doom and gloom and everything's going to fall apart. But the reality is that most of it works, but there's like this little annoying percentage that never really works, and you don't know when it's going to show up. And it's because we're not monitoring actually key parts of the process. So we can go to the next slide, Joel. So how does this thing actually work, right? So Tobias had actually mentioned contact angle, all right? And contact angle is something that BTG Labs has used in our surface analysis lab for a long, long time. And it can be a great technique, but the problem is that traditionally it hasn't been packaged and industrialized in a way that allows us to use it in the manufacturing floor. And we do this in a pretty different way than traditional contact angle techniques, all right? What we're actually doing is we're printing the droplet onto the surface, all right? You can see this little GIF up here, and yes, I say GIF, I don't say GIF. The little GIF up here, we actually build a droplet through a series of micro droplets, okay? And what this does is this puts kinetic energy into the droplet. It overcomes roughness, right? So it overcomes different morphology. We can shoot this thing vertically. We can shoot it upside down into channels, on curved sections. So it makes our measurement extremely repeatable and very, very flexible. And the whole thing happens in about 100 milliseconds. You can go to the next slide. So when this is, oh, okay, sorry, I've skipped a slide here. However, what's cool about this, all right, is if we understand what a surface is and what it means for adhesives and coatings, we can actually apply a number that we put to that, the shape of that water droplet that it makes on the surface, to the state of that surface, all right? So let's take, for example, a metal component, all right? And we machine that metal component, or maybe we laser etch it or laser ablate it, okay? And when we do that, we have literally fractured molecular bonds, right? We've ripped molecules apart, all right? And we have all these reactive molecular sites right there. Within milliseconds, we get an oxide layer that begins to build. Then we get a little bit of water vapor, some hydration, all right, hydroxyl groups. We then begin to get some contamination after that. And every time we have essentially a molecule attach itself to that metal surface, we lose some reactivity, we lose reactive sites, all right? And as you guys go out and Google some of this, you'll see the jargon really of this process, and it's really called surface energy, all right? And surface energy is just the total amount of chemical reactivity that's present on a surface for it to do work, all right? And surface energy in and of itself doesn't necessarily predict adhesion, but it's an extremely sensitive way to understand, is my surface the same? Where am I on this scale, right? Am I still at kind of my native oxide layer, or do I have a bunch of organic contamination on this thing? And so all of a sudden you can start setting objective standards and statistics based on what a surface should be at a particular manufacturing point. So it's a really, really great way to understand this and monitor it. There's really kind of two key ways that you use measurement technology in manufacturing, right? One of them is for monitoring, and the other one's for analysis. And we can apply this in both scenarios, but the monitoring piece is really where we get to the point where we're not producing, 7%, of our failures being glue related, for example. So this is very, very thin, right? We're talking like a real thin area of the surface. Sorry, go ahead, Tobias.
Oh, I'd be curious from the audience here, who before has used this water contact angle to evaluate a surface, and what was your experience? Did it work well? I've seen a pretty wide variety of successes and failures of using this. I think it highly depends on the system and how well you've thought out the test beforehand. It's not a simple test to get reliable results from.
Data interpretation, that analysis piece of contact angle, traditionally can be real tough. It historically can be tough to do, right? If you don't have really good contextual knowledge around the materials and processes that you're using, it can be tough. It really can be tough to discern. And so that's why I'm really breaking up two things here. One is the monitoring side of things, where we can say, hey, are we in a particular range? And then the other side is the analysis and saying, hey, look, my average dropped 10 degrees. What's that mean? Why did it do that? Or my standard deviation is now much higher. Or, I made the surface rougher, but my contact angle didn't go down. Does that mean contact angle is not working? Right? Like these are the types of questions that we'll get around that. So.
Great. Looks like we have a few people that have tried it before. With some, let's see, Emily had some inconclusive results. Jessica had a good indicator, but hard to characterize large surfaces. Yeah, I think it is a valuable tool, but it has to be done right to have actually conclusive results.
Yep, 100%. And that's, the experience and expertise that we're going to provide and give to our customers who invest in this piece of technology is really where we can take, say, the development guys and take them from using it a little bit and trying to understand that data to the point where they really understand how it's working and how that happens. So we can definitely get into the weeds on this, but certainly this is kind of the 10,000 foot view. So Ahmed actually has a really cool question here that we'll get into just a little bit, but basically, right, as the higher energy our materials are, the more they attract that water droplet to the surface. So the more that water droplet's going to wet out. The less energy that's available on that surface, the water molecules are more attracted to themselves and to the surface. And so it's going to start to beat up. All right. And the number that we return is the angle that the perimeter makes with the surface. The lower the value, the more it's spreading out. The higher the value, the more it's beating up. Because it is sensitive to the top 2 to 5 molecular layers of a material, some variability is normal. It can be tough to create surfaces in manufacturing that have variability better than ±2. The best that we ever see is on silicon wafers, which we can get to ±1. But like an industrially prepared surface, like something that's solvent wiped, say a piece of aluminum or polymer that's solvent wiped, ±4 degrees is pretty normal. So how do we apply this, right? We've talked a little bit about this. The PD or R&D uses this to help set standards on what surfaces should be where they've gotten good results with their adhesive or their coating. QC auditing can take that information, right? Once it becomes, say, process of record or in the drawing, they can take that information and use it to make sure that as they go through ramp and as they're producing over time, things aren't changing and things are as they should be. And then obviously we've got the in-process monitoring piece, which allows us to get some statistical trends and really make sure that we've got an IQC spec and OQC spec that allows us to make sure that we don't get failures, certainly in the field, right, at the consumer level.
All right, let's talk about a real world use case, an application. An instrumental customer, P2I, they developed this nano coating for waterproofing electronic devices. It's actually pretty impressive. It's a little different from traditional waterproofing. They expect the water to get inside the device, and then they nano coat this very thin coating over all of the critical PCB components to prevent shorting and corrosion. And what this means is the coating quality has to be perfect. Otherwise, the whole functionality of the coating is gonna degrade. So very, very tricky application, and they were struggling to find a quality control system that could address this. And so that's when they came to Instrumental. Lucas, have you seen a lot of these nano coatings coming up recently?
I mean, certainly, right? Everybody's looking to try, certainly anything that's going to be operated in the environment has to have, I'll just say moisture protection or moisture barrier, right? So traditionally conformal coating has been done for a long time on PCBs. That's one way to accomplish this. But then you've got this other piece where like you have multiple components that have to come together, and then you kind of want to also coat the outside, right? To just help from water ingress in general. So we're seeing more and more of it, right? It's just becoming really important.
It is, and just as an industry too, like we were talking about, going towards more and more environmental protection is something that the consumers want.
Mm-hmm.
All right, I do see lots of great questions coming in. A good one from Ryan as well about IP water ratings and what types of adhesives are needed to achieve that. We will touch on that at the end. Let's see. So Instrumental. Let's talk about what we do with this data. The Surface Analyst system is collecting all this great data, and for P2I. Instrumental was used to collect data across the supply chain. So from upstream suppliers in their factory, we had multiple image collection points. So you can see here in the middle, before their coating was dispensed, right after it was dispensed, and also downstream. So this is what Lucas was referring to, having those critical control points so that you can actually trace down and pinpoint the root cause of an issue. And so we take all this data and then we centralize it in Instrumental's cloud database. And then on top of that, we analyze it with our machine learning algorithms, proactively find new issues, and then help your team quickly and efficiently solve those issues with the end goal of keeping your program on schedule, avoiding delays, and shortening that overall product development cycle. And so with P2I, if we hop to the next slide, we can look at some actual images here. So this coating they had, again, we talked about how difficult it is to inspect these coatings. You can see on that first image on the left, it's coating around this board-to-board connector, and it's this very amorphous glob that's pretty hard to define what is overflow and what's not. So P2I, they had tried visual inspection, but of course, that's a little bit subjective. There's tons of things to inspect. And the other vision systems, weren't performing to the level that they needed. And so that's where instrumental system came in. And even with all of these extremely funky defect types, you can see the second one, there's some contamination. The third one, it's kind of overflowed up to the top. And then the fourth one, it's only covering the right side of the board to board. And then on the left, it looks like they missed it. So huge variety of defect types. Lucas, have you seen other systems or similar defect types to these like abnormal blobs?
Yeah, I mean, typically, so like in coding applications, when we're looking for, and this is really pretty true for whether it's conformal coding or even painting, we're typically not running into problems where like sheets of a coating are just kind of flaking off. It's usually it's like bubbling defects or fish eyes or de-wetting. Different applications will use different jargon to describe very similar failure modes. But we'll see kind of like in the painting world, it'll be like an aesthetic defect where you get what they call orange peel or fish eyes. And that's almost always from surface contamination. It's just you don't have the appropriate wettability parameters to get that coating to wet out well, or you might have a thickness problem. Certainly on paints, right? The thickness is much thicker than what this is doing. Also, too, when you get like real thin, then you have a hard time not developing pinholes. And that's not even necessarily a surface energy issue. But not having on like real thin nano coatings, for example, pinholes can be a real issue too. So yeah, I mean, totally, all kinds of stuff can pop up.
Yeah. All right. Let's go on to the next one here. And again, so individual defects, their entire board had a crazy number of different components and dispense patterns. And so it's a whole lot for either a manual operator, or if you're going to try to pre-program, it would just be unfathomable, a number of different tests. So instrumental system, the AI, it just looks through all the images for you. You can see here on the grid, and it highlights automatically areas where it finds an anomaly. So it's proactively identifying these new issues for you. Again, because you might not know exactly what that defect in the glue is going to look like, because each time something new presents itself. And like, that's just the nature of glue, is it's very hard to inspect. So they were able to find these issues early. And then, and another key part about this, the P2I team was actually fully remote while they were doing this development. So Instrumental served as a centralized collaboration platform. So their factory was over in China. Their headquarters was in the UK. And then they also had some remote team members in the US. And so they were going through this product development cycle completely remote. So they took all this data in the Instrumental system, and from there they had dashboards. Joel, if you kind of progress a couple here, they had dashboards to allow them to monitor their quality remotely. They were able to tune the processes using these images, update some of their dispense patterns, again, remotely. Quality team could monitor the top issues. And then in the factory as well, they were using it for a live go, no go for some of the defects. And the results.
Tobias, I'm sorry to interrupt, but there was actually a question that I personally had. I mean, on average, how many images do you guys have to take before you can start making some or having the AI make some determinations about what the hotspots are?
Oh yeah, great question from Emily there. So our system, it's actually designed to be used early on in development. So we just need 30 units to get started. So with P2I, for example, tuning their processes early on, starting in prototype and EVT builds when there's a lot of variability earlier on in the process, so they can tweak in those processes. Mm-hmm. And same if we're, again, ingesting data from the Surface Analyst, we don't need that many data points. Just getting 30 units, you can start to find correlations between images and maybe some of the outcomes of the surface properties or some adhesion pull tests later on. Mm-hmm. Let's talk about the outcomes here. So again, P2I was setting out on this new development of this novel technology. Their teams are remote, and they were able to, with the instrumental system, they were able to successfully make it through their product development on time and actually ship this new technology. Their efficiency on their engineering team tripled due to being able to use this tool. They were able to reduce the in-person operator headcount. So not only is it a more reliable inspection than the visual inspection, we're actually able to reduce the headcount, as well as reduce the quality escapes that were making it downstream, where we also had instrumental coverage, so we could kind of trace it. And again, the impressive part is all of these metrics were hit during the pandemic. All of this was done remotely. Supply chains were getting disrupted, but they were able to get all these improvements by properly utilizing this data and utilizing this tool for remote management.
Nice. And I like how you phrased that, Tobias, regrettable rework. All rework is regrettable.
Regrettable rework, yes.
It's always regrettable.
All right, excellent. So we hit on a lot of things, kind of the best practices for setting up your line for collecting the data, for optimal adhesion, some actual applications, some different tools that you can use. I know we have some questions in the chat already, but we would love to keep them coming. And I think you might even be able to come up here live to chat with us if that's on the docket as well. So please, questions, again, either in the Zoom chat, or I think there's actually a Q&A. We've got a couple coming in. Let's see. So Barry, can you discuss the various surface preparation techniques to increase surface activation? Yes. I think Lucas, that'd be a great one.
Let me take it, please. Let me take it. No, one thing I wanted to mention, guys, when you're doing a joint webinar like this, we can only hit the 30,000 foot view. Surface preparation is a topic that's near and dear to my heart. All right. We help people all the time do this. What you leverage and how you leverage it, the engineering answer is it depends on the substrate, depends on your supply chain. We're big fans of things like laser cleaning for metals. We are big fans of things like plasmas and different surface activation techniques for polymers and composites. You can set up, there's many tools in the toolkit for getting to a good surface, or what we're defining as a good surface. What you do and how you do it depends on what you're building, how many parts, how it's distributed, et cetera. We've helped customers be extremely successful just wiping with alcohol. If you can clean to a number, I can make sure that John does the same thing as Sarah, that does the same thing as Jim. And I can tell exactly when people are slacking off a little bit and they start wiping this way instead of in one direction and folding the cloth. You know, that's on the one end. The other end is I can tell, hey, I've got an atmospheric pressure plasma system by understanding what my outcome is and what it should be. Oh, hey guys, when I plasma treat this appropriately, I get between 20 and 30. I can see that nozzle degrade over time because my standard deviation starts climbing, right? If I look at my SPC chart. So you can actually tie that back to maintenance cycles in, say, more automated surface prep processes. All kinds of little caveats and things that you need to be aware of for optimal maintenance of a surface prep system.
Thank you, Lucas. Let's see, we've got a couple more questions, but before, as promised, highly requested, another manufacturing glue joke. This is courtesy of Joel. I can't take credit here. What is an adhesion specialist's favorite type of home? Anybody? An igloo.
Dude, is Joel just coming up with these on his own? This is amazing.
Igloo. Right. Another groaner. So let's go back. We had a question from Chris back at the start. With the right to repair movement picking up steam, how can we design with glues in a sustainable, repairable way? Yeah,
this is an awesome question. I would like to take a stab at it, Tobias, if you don't mind.
Yeah, start us off.
So if I think about right to repair for electronic devices, like, you know, your phone, right? Your phone. So I've got a screen, I've got stuff on the back of the screen, I'm putting this thing into a housing. And when you got to repair it, what are you doing? You have to pull that apart, okay? Or your screen cracks and you're replacing the screen. And let's say I'm bonding that display to my housing. Well, I basically have 3 links in the chain, right? I have the display glass as one link. I've got the interface between the display glass and the adhesive as another link. Then I've got the interface between the then I got the adhesive itself. Then I've got the interface between the adhesive and the housing. The system is going to fail in the weakest link. And if I'm thinking about, I want a glue joint because of all the engineering benefits of this thing, or like the aesthetic ones, right? I can like make my displays as big as possible. I ideally have a system that fails within the adhesive when I pull it apart. And the reason for that is if when I peel this thing apart, if the adhesive is what breaks first, that's where, you know, your force gets transferred into it, that's the weakest link in the chain. I now have a surface that I can really easily reapply adhesive to get the thing back apart. All right. The other way that you could look at it is if you can design one that peels at the interface, that could also be a possibility. But the issue with that is usually if you're peeling at the interface, you don't have a super strong glue bond as it is. And so you could have something that might be a little bit less robust. It's a tough challenge. You know, I remember early on being at Lockheed Martin, and they had a company-wide engineering contest on figuring out a fastening system that would perform like an adhesive, but was also removable and like repairable. And that's a tough challenge. You know, that's it. That's my comments, I think.
It's a hot question. It's a hot question. It's a constant debate of when you're designing a product, screws versus glues for fastening things together. I don't think there's a clear-cut answer. I have kind of a few philosophies to consider when selecting for each individual application. I think, Lucas, to your point, at least considering and thinking through what the repair of that specific component would look like. At least going through your mind, is there a better fastening solution that might be able to be taken apart versus just giving it no thought and going for maximum strength as the only metric? So step one is just considering that for each of the take apart steps. And practically speaking, what I've seen is glues are much easier to kind of ad hoc add in as a Band-Aid later on. This is just from personal experience, is glues often get thrown in later in the development cycle to fix something that wasn't working before. So if possible, earlier on when you're actually designing the product, try if there's any fasteners or anything else that you want, optimize for that early on, because the glues you will spend a lot of time tweaking later on, and that is always an alternative option with less sort of upfront geometric design constraints.
That's a really good point, Tobias. It is easier if you have an assembly, if you have a joint, and it's not a joint at the beginning really, but if you have a joint that's designed to take fasteners, and then you decide, it's easier to go to adhesives with that joint than to go from a joint that's designed to be adhesively bonded to fasteners. Yep. I would be a generally good rule. That's a good way to put it.
All right, let's see. We're getting really close to time here. Any final questions, please post them in. We had, I think, one or two more on the list. Let's, from Ryan, can you talk about the adhesive waterproof IP rating and what adhesive methods would create waterproofing or prevent water ingress? And what about gaskets? That's a great question. I've got a few comments based on my experience, but Lucas, anything you want to share there?
I mean, I'm not going to sit here and say I've got the answer, right? Like, oh, use adhesive XYZ, but I will say this, like typically there's various RTV silicone sealants that are used in the automotive industry to keep oil where it needs to be and water out of where it shouldn't be. Various different flavors of that, various different curing profiles, curing mechanisms, but they're typically pretty strong once they're cured up, and they typically don't need very thick bond lines, but they're a little messy. So, you know, pros and cons to everything. I don't know. I'd say probably look at an RTV solution. They use liquid gaskets all the time for different things.
Yeah, I think in my experience with a variety of different Apple products, we've achieved environmental seals to the different kind of either IPX6, IPX7, like splash-proof, waterproof rating. We've achieved seals with most of the different types of adhesives. If it's either a pressure sensitive or a heat activated film or some type of liquid glue, all of those are capable of achieving that. I think it's dependent on the specific application and the other requirements surrounding it, and kind of what we alluded on before, your ability to consistently control that process. Like most waterproofing failures don't happen 100%. Most of them happen because what you've designed for is not easily able to be controlled. Yep. And then 1 or 2% or 5% of the units end up failing that waterproofing spec.
Yeah, if you've got one small little void, you know, for whatever reason, one section of the material is a little contaminated, so it doesn't wet out perfectly. If that goes into a leak test, that's where it's going to fail. It's not, and it'll be like one small percentage of the overall joint. You know, we'll see that a lot. So it's yeah, I think you're right. Controlling for consistency. Consistency is more important than ultimate performance, really.
Yes, exactly. But it is a topic to be considered in the design of your glue joint.
Right.
So when you're designing, it's not just, oh, all right, HAF meets on the spec sheet, meets my nominal requirements to waterproof and strength. It should be considered, how do I, what contaminants is this affected by, what surface quality is needed, and can I maintain that control throughout the life cycle? So that would be my only advice. Awesome. All right. I think we got some interesting anecdotes from Michael. I think we are right at time here. I do believe there's a survey that we would love if you guys filled out right when you leave this. It's very valuable for future webinars. Anything else you want to add, Lucas, before we wrap up here?
Oh yeah, I mean, please fill out the survey. We want to keep creating content and sharing things with you guys that give you tools to build better products into the future. And obviously on any of these topics, if you want to get more in depth, feel free to reach out.
Yeah, thank you. Thank you all for joining and learning and talking glue with us.
Love it. Thank you. Thanks, guys.
Thanks, everyone.